This is FRM Part 1, Book 2, Quantitative Analysis, and the chapter on sample moments. Let's start with the first word in that title, sample. You guys have been watching my videos know that I like to give what I consider to be interesting examples. Some people might call them silly, but they're all relevant to what we're trying to do here. Here's my introductory example for this chapter. I love to eat grapefruit. I love to cut up grapefruit for my children. They love to eat it because it's good and it's good for them. But the problem is that when you cut open that grapefruit, there are bunches of seeds in there. And let's suppose that we're researchers and we want to figure out about the number of seeds in a grapefruit. So what we do is we go to the food store and we buy thousands of grapefruit, right? And we come home and cut them and we slice them up and we see some have 3 or 4 seeds, some have 6 or 7 seeds, some have 10 or 12 seeds. So you have 1,000 of these grapefruit and you list each number of seeds for each grapefruit. Well, that entire sample is probably not very informative, right? It gives you a range maybe, and it gives you kind of a sense of what to expect when you cut open a grapefruit. But what we need to do is look at the second part of that title, the moments. We're going to try to find the moments of that sample that can inform us about future consumption of grapefruit. And of course, that first moment is the average or the mean. So we can take those 1,000 and divide by 1,000 and we'll get, let's say, 5 seeds. And when we cut open the next grapefruit, we know that we're probably not going to get 5. We might get 5, but maybe we'll get 3 and maybe we'll get 7. So some are going to be less and some are going to be more. And that leads us to those other moments. And so here's my quick summary of my initial silly example is that these moments, and there are going to be 4 of them that we'll talk about today, are going to help us give an idea of what the distribution of that sample might be so that we can make decisions about future grapefruit consumption and the number of seeds that we can expect. All right, let's look at these learning objectives. Notice that there are no grapefruit words in these learning objectives. Thank heavens for that. All right, so what are we going to do? We're going to do a lot of estimating here. Mean, variance, population moments, sample moments, estimators, and estimates. We're going to try to decide whether or not these moments are biased or not. You know, what if we came up with a moment of the grapefruit sample that said something like, you know what, every third grapefruit is going to have 50 seeds. Well, that doesn't sound pretty normal, right? It doesn't sound like it's within the reasonable expectations about seeds in a grapefruit. So we're going to worry about some that are biased. Then we'll talk about the central limit theorem. And then we'll get to the third and the fourth moments of the distribution, which are skewness and kurtosis. And then we'll end with some covariance, correlation, co-skewness, and cokurtosis. So this ought to be a fun slide deck. Now let's swing back to my example, right? What did we do? We bought 1,000 grapefruit from a store. That was a sample. It's clearly not the population. In order for us to study the population, we would have to go all over the world. Geez, I don't even know how many places grow grapefruit, but we'd have to get every grapefruit that is out there. That would be the population of grapefruit. Now, what we're interested in, of course, is the population parameters, like a mean and a standard deviation. Those are the first and the second moments. But, geez, you think about what kind of a headache would that cause us if we had to travel around the world to get all of the grapefruit. So notice what I have in that second block point. Nearly impossible to study the population itself. Well, I'm going to go out on a limb and say it is completely impossible to study the entire population of grapefruit because, you know, by the time you went to Florida and by the time you went over there and by the time you went over there and you collected all the grapefruit in the entire globe, some other grapefruit probably would have grown during that time. So you really can't keep up with that. Look at that circle point. Imagine having to collect performance data from every hedge fund that's available out there. So instead what we do is we take pockets of the population, and those pockets are called sample. And we're going to evaluate the sample moments mean, standard deviation, skewness, and kurtosis. And that's pretty much what we're going to do in this slide deck. Now imagine you have these 1,000 grapefruit on your kitchen table and you want to figure out what is the best guess based on your sample of what's happening in the population. All right, so we have a point estimate is the result of using an estimator to find the value of the population parameter, right? So you're estimating, you have these 1,000 and you're trying to say, based on these 1,000, my best guess for the overall population is going to be something. All right, so look at this quick example. If we want to know what the average return earned by the hedge funds in the United States, we would compute the sample mean. We would take a sample, maybe 30 hedge funds, maybe 100 hedge funds, but what that's going to be is an estimator for the population. Now, if we go ahead and get our financial calculators out and hit some buttons and calculate that sample mean, and let's suppose it's 15%, we would say that that is our point estimate. Now, there's a quote down here at the bottom from an introductory econometrics textbook here. An estimator is like a recipe in a cookbook, and an estimate is like a cake baked according to that recipe. And that's a really good and really simple analogy. Of course, it probably has more meaning to those of you who actually cook. I don't do a whole lot of cooking. I do some grilling, but I'm not sure how that relates to statistics, but somehow it does. All right, so look at the top up here. We have these unknown parameters in the population, right? Since we can't collect all of the number of grapefruits in the world, we don't really know what that parameter, what that population parameter it is, and we don't know what that probability distribution is going to be. So what we do is we collect a sample, x1, x2, all the way out to x30 or 50 or 1,000, right, in our grapefruit example. And then we use an estimator. And notice that at the very top, I have the unknown parameter theta, but down at the bottom in the bolded blue box, I have the estimator is theta hat. So when you put a hat on top of a parameter, that is a signal that it is the best guess of that population parameter. All right, and so note down on the right-hand side over there, we're going to use probability theory and we're going to use statistical inference. We're going to take our sample of 1,000 grapefruit and make some conclusions about all of the grapefruits. Grapefruit or grapefruits? Not sure what the plural is. Maybe that could be your homework assignment. All right, of course, we don't want to come up with biased estimators, right? A biased estimator would be like a mother or a father who is the coach of their son or daughter's team and always saying things like, oh, my son or daughter is the best player on the team. That, of course, is a biased estimate of the talent level of the child, right? So we want an unbiased estimator. If this is a soccer team, we want to get a really good man or woman who knows everything about soccer to come in and say something like, hey, this is where the talent lies on your team. That would be an unbiased estimator. All right, so notice at the very top there, I have the expected value of theta hat equals theta. That's the definition of an unbiased estimator. What that means is that it guarantees that on average, that true value of the population parameter theta will be realized inside of the sample. And there's a good picture down there. Look at the left-handed normal distribution with the true parameter right there, theta in the middle. And if we estimate the theta hat all the way over here to the right, on the right side of that red line, boy, look at the PDF has shifted all the way over. So of course that's going to be biased. We don't want to have any bias when we're analyzing our 1,000 grapefruit to make a judgment on the population of grapefruit. Now, I'm guessing you guys know everything there is to know about the first moment of the distribution, the mean. You learn this at a very young age, calculating the mean. So all we're going to do is we're going to sum all the values, right? We have 3 seeds and 5 seeds and 12 seeds. So we have 1,000 of these. We sum them and divide by 1,000. What we say then is that that sample mean is an unbiased estimator of the population mean. Now, quickly, let's go ahead and say that the sample mean is probably distributed with the mean of mu and then a variance of sigma squared over n. And we'll talk about the importance of dividing by n when we compute these moments here. And we'll have a couple of examples. Let's start with sample scores of FRM candidates in a mock exam. So we have some scores down the left-hand column, and then there's a frequency. So what is 4 plus 3 plus 2? That's 9, and 1 and 1, that's 11. So we have 11 inside of this sample, and to compute the mean, we'll just add those and divide by 11, so that mean is 65. All right, so let's go ahead and summarize what that 65 means. On average, it's going to be equal to the population mean, and it tends to be closer to the population mean as the sample size increases, and then it's going to be assumed to be normally distributed. We'll talk a little bit more about that in a second. Now, remember, my econometrics professor in graduate school emphasized this concept of BLUE, the best linear, unbiased estimate. So it has to be linear, right? Has to be unbiased, and has to be efficient. And efficiency here means solely that it has the least possible standard deviation, or in bold there I have the least variance. So this is the conclusion that we make. The sample mean is the BLUE estimator of the population mean. So whatever we got on our kitchen table, what did I say earlier? 5 seeds was our average. That's our BLUE estimator of the population mean. Now, how about if we move on to the second moment of the distribution, which technically is the variance, but since the variance is a squared number, we take the square root of the variance and get the standard deviation. So let's go back to my example. You know, what was the mean? 5. So some are going to be less than, like 2 and 3, and some are going to be greater than, like 7 and 8. And what the standard deviation measures is how far away from the mean are each of those observed numbers of seeds inside of each grapefruit. And so notice what you do. You take the 3 minus the 5, right? We observe 3 minus the mean, and then we square it. And then we take 4 minus the 5, and we square it. And then we take 7 minus the 5, and then 12 minus the 5. And we do that 1,000 times. And the reason that we do that is simply to get rid of the negative, so that some that are lower than 5 don't exactly offset the sum that are higher than 5. And that square takes care of all of that. Now notice in that top formula I have there, I have n in red. And it looks like we're going to divide by n. And that's true in our first step here. Notice at the top I have the sample estimator of the variance is defined as the sum of all those differences from the mean squared divided by n. Now, if we divide by n, the variance is going to be a biased estimator of the population variance. And there's the biased equation there. It's going to be equal to the difference between the n minus 1 over n. And I'll talk about that in just a second, minus that variance. And so look on the far right there. There's the bias, sigma squared over n, right? But what we need to do is, instead of dividing by n, we need to divide by n minus 1. Those of you who are familiar with statistics ought to remember that that n minus 1 is known as the degrees of freedom. And if you do a search for degrees of freedom, you get all kinds of statistical kinds of definitions. Some of them make a little more sense than others. Some of them, you have to scratch your head and you have to think, all right, I really need to know a lot about econometrics to understand that definition of degrees of freedom. But let me give you the simple example here I always give my students. Let's suppose that you take 2 of my exams. On the first exam, you make a 10. On the second exam, you don't know what you got. But you do know the mean on your 2 scores is 15, right? So you took 2. You don't know the score on your second. You know the mean is 15. So if you made a 10 on the first test, then you know you had to have made a 20 on the second test to get a mean of 15. So how many tests did you take? 2. But if you know that first moment, you only need to know 1. You don't need to know both. You only need to know n minus 1. So we're going to divide by the degrees of freedom to get that unbiased estimator. And here's how we're going to do it. So let's use that same sample data going down the left-hand side. We know the mean is 65. So what we'll do in the third column there, we'll take the 4 60s, right? There's 4 frequencies of the scores of 60s, minus 65. That gives me a minus 5, right? So we have 4 of them. We'll square it. So that gives us those 25s down that far right column. And then we'll do that all the way down to the bottom, and notice that that total is 270. So to get the variance, we're going to take 270 divided by not 11, but degrees of freedom. So let's go ahead and do this here, right? If you take 11 of my exams and you know the mean is 15 on those 11, all you have to do is know the first 10 scores, and you can work your way back to figure out what you had to have gotten on that 11th score. I know that's a little more complex to kind of visualize that than my 2-test example, but the same thing applies. So the variance is 27, take the square root of that, and we get a second moment of the distribution. We get a standard deviation of 5.2. So mean of 65, standard deviation of 5.2. And let's go ahead and spend just a moment on the interpretation of that standard deviation. What that means is that if you randomly sample these test takers, you expect to get to observe a score of 65, right? That's the mean, that's the unbiased estimator. But you know that you're going to be wrong on average 5.2. So sometimes, let's just round that to 5. On average, you're going to be wrong 60, right? That's 5 away from 65. And then 70, that's 5 away from 65. You have to go on both sides. Remember, we're thinking about what kind of a distribution. I want you to think about a normal distribution. So there's the mean in the middle, 65. So we're moving some to the left and some to the right. Actually, that standard deviation is going to be a great measure of total risk for us. Now look in the very middle of the bottom of the page. There's our bell-shaped curve. That's a symmetrical normal distribution in which the mean and the median and the mode are the same number, right? Well, does that mean that every distribution is going to be normal? And of course the answer is no. Sometimes we can be a little tilted one way or a little tilted a different way. Skewness measures the asymmetry of the distribution. So notice on the left, where the mode is less than the median, which is less than the mean, right? Median's always going to be in the middle. That's positive skewness. Then over on the right, we have the mean, which is less than the median, which is less than the mode, and that's called negative skewness. So just think about, kind of a tilt to the left and a tilt to the right. Skewness measures that level of tilt. Let's go ahead and calculate the skewness from our previous example. We know the mean is 65. We know the standard deviation is 5.2. So what we want to do is compute the third moment of the distribution. And this is really just almost an identical calculation as the variance. But notice at the top right on that fourth column, I'm going to take each individual score minus the mean score, and then I'm going to raise it to the third power. This is called the third moment. Skewness is the third moment, right? And then we sum all those things, divide by 11, and then we're going to divide by sigma cubed, which is standard deviation raised to the third power. So we get skewness of 0.578. So the skewness in this case is not 0, right? Let me go back here. With the symmetrical distribution, we'd have a skewness of 0, but now we have a skewness that's 0.57, so that's positive. So we have a distribution that looks like that positive skewed distribution on the left. And this has tremendous implications for us in risk management, because what that means is that we're going to tend to have more observations that fall to the left, right, than fall to the right. Oh, we need to worry about tails. We'll talk about that in future chapters. All right, how about the fourth moment of the distribution? This is called kurtosis. And while, here, let me go back and do this. While skewness measures, kind of the tilt to the left and the tilt to the right, kurtosis is going to measure how high the peak is and then how heavy the tails are. Look in that middle graph, the bell-shaped curve, the height is a normal distribution, but some distributions will be above that and some will be below that, and some tails will be heavier and some tails will be skinnier. And that's what kurtosis is going to measure. Now, what kurtosis does is it brings in the specter of outliers. Going back to my example of seeds, right? What's an outlier? 0, right? If there are no seeds, then you're going to observe 0. And that's probably pretty close to 1 and 2. So that's probably not an outlier. But suppose you have a grapefruit that has 100 seeds in it for some crazy reason. Well, kurtosis is going to measure that outlier. Now look at the bottom, the check marks I have. Leptokurtic distributions have a higher peak. Platykurtic distributions have a lower peak. And then the normal curve is mesokurtic. These are really hard words to pronounce. All right, let's go ahead and compute the kurtosis here. So what we're going to do is the same thing, right? We're going to take the difference between each observation and the mean, and then we're going to raise it to the 4th power. We're going to sum those again, then we're going to divide by 11, and then we're going to divide that by sigma raised to the 4th power. So we have kurtosis in this case of 1.87. All right, let's swing back to my grapefruit example. We've got 1,000 of these laid out on our kitchen table. And what we might want to do is we might want to chop them into different parts. So what we could do is we could chop them in half, right? We could say, here's the middle value. Everything less than that is over here, and everything greater than that middle value. So we would divide those into quantiles. Quantiles kind of the general word for how often do you want to chop those up. Do you want to chop them in half? Do you want to chop them in thirds, or in fourths, or in fifths, or in tenths, etc., etc.? Notice in the middle there I have the median, and so there's the function for the median. And then one of the things that's really interesting for researchers to take a look at is this interquartile range. So what we can do is we can chop them into 4 and then look at what happens in the middle. That seems to be kind of the focus for lots of researchers, not just financial researchers, but lots of researchers is, what happens in the middle. Now, of course, for us as good financial risk managers, we're going to want to know what happens in that left tail. That's when we're going to bring in this concept of value at risk, which will be a really fun conversation that we have later on. Let's go ahead and spend a few minutes talking about the median, and because this calculation is kind of interesting because of the following, right? What did we have? We had 1,000 observations, but let's go back and just suppose that we have just 3 grapefruits, right? 3 grapefruits, 3 grapefruits. If you have 3 of them, right, and one has 3 and one has 5 and one has 7 seeds, the median is going to be the one in the middle, right? So if the number of observations is odd, you just put the same amount on this side, the same amount on that side, you leave one in the middle, and that's going to be the median. But if we have 2 grapefruit and one has 5 and one has 7, well, what you have to do is cut in the middle in half, and so you would go with 6, and that's what those two equations look like there. And so notice the properties. It may not be an actual observation in the data set if you have an even number. All right, it's not affected by extreme values, and it's a midpoint, especially when there are large numbers. So let's go ahead and and compute the median here. So notice what we've done. So we have, we've been dividing by 11 before. So, right, we have 11 of these. So, you go 5 on the left and 5 on the right. And so there's the median, that's 64. All right, what we've done so far is take a look at these moments, right? First 4 moments of the distribution. Now remember that I was saying that some of those observations are going to be to the left of the mean and some are going to be to the right of the mean. Well, this brings up an interesting question. Can we decide on any type of reasonable conclusions about what's going to show up on the left or what's going to show up on the right within some normal range? And this is what the central limit theorem tells us here. So note, if we're going to draw a simple random sample size n from any population, right? So what was the population of grapefruit? We really don't know. Maybe it's 1 million, maybe it's 1 billion, but we had a sample of 1,000, right? But this population, it's going to have a mean and it's going to have a finite standard deviation. But here's the deal. When n is large, when our sample is large, like 1,000, that sounds like a large sample size. When we observe the seeds in 1,000 grapefruit, that sampling distribution of the sample mean is approximately going to be normal. In fact, as we go to 2,000 and 3,000, that distribution of the sample mean is going to be even closer and closer to normal, because we can take 1,000 from I shop at the Giant, that's our store here, and then we also have a Weiss Markets. I can shop at that store. We can go to Wegmans, and we can go to all these different stores and buy 1,000 of them. And so we can continue to calculate the sample of each of those grapefruit from each of those different food stores. And then what that means is that the sampling distribution of all of those means is probably going to be pretty close to normal. Here's kind of summary of what I've been saying here. If the sample is normal, then the sampling distribution of the X bars, they will also be normal. However, when the sample population is approximately symmetric, then, oh boy, it's going to be approximately normal. I'm always leery when I hear that term, approximately something or nearly something. But in statistics, it really holds true. It's approximately normal for small values. But if you add skewness to this, then you got to get up to that traditional number of n being 30 before it becomes approximately normal. Let's take a look at a quick example here. Certain brand of tires, mean life of 30,000 kilometers with a standard deviation of 3,600 kilometers. What is the probability that a mean life of 81 tires is less than 29,200 kilometers? Well, what do we know? Mu is 30,000 kilometers, right? And standard deviation is going to be 400 there, right? So what we need to do is get out our z-score. So here's our z-table. And we can compute the z. That's a pretty simple calculation. There's 2. And so what we're going to do is run our finger down the z, and we get the 2.0. And so it's 2.0. We don't have to run our finger all the way across. And by the way, whenever you're on exam, make sure you know which half of the table. Most tables that are provided for examinations only contain half because they're mirror images of each other with a normal distribution. This is why for my students, especially in derivative securities, when we're computing the Black-Scholes-Merton option pricing model, I give them the full table so they don't have to worry about going to the left or to the right. Anyway, if you do all that, you see that probability is around, what is that, 97725. Subtract that from 1, and so that probability turns out to be 2.275%. So there is, here, let me go back here. So our mean is, what's our mean? 30,000. And so the probability that we're going to experience less than 29,200 kilometers is pretty low. And so what do we say? It's about 2.2%. Now, what we've been doing so far is taking a look at one random variable, like scores on the FRM exam or seeds inside of a grapefruit. But of course, we're going to try to study 2 variables, and we want to know what the relationship between those 2 variables are, like the level of interest rates, and the level of inflation. Now, just from our regular knowledge of economics, we know that inflation is an integral component of interest rates. So these two variables, these are two random variables, they probably have a high degree of a relationship. So we need a measure to evaluate how these two random variables randomly fluctuate together over time. And that's called the covariance. And so to compute the covariance, all we're going to do is take the distance between each observation and its mean and multiply that by the distance between each observation and its mean. Of course, the first difference is for the first random variable, and the second difference is for the second random variable. That's why we call it a covariance. And there's the sample covariance estimator, and notice the notation sigma hat sub xy. Xy are the two random variables. Now, let me go ahead and remind you of the need for dividing by n minus 1 rather than n. So to have an unbiased estimator, we'll divide by n minus 1. All right, let's take a look at a quick example here. Let's suppose that we have two assets, asset A and asset B. So those are the returns going down the left-hand column. And then we have three states of the economy. We've got a strong, a normal, and a weak economy. And there are the probabilities associated with those economies. So 15% strong, 25% weak, that gets us up to 40%, right? And then the normal economy is 60%. So those probabilities all have to sum to 1. So how do we establish the covariance between the two assets? All right, well, the first thing that we're going to have to do is compute the mean, the first moment of the distribution. All right, so we'll call that the expected return of each asset. So we'll just take 15% times the 40 and the 20, right? Then 60% times the 20 and the 15, and then 25% times the 0 and the 4. And that gets us an expected return on asset A of 18% and an expected return on asset B of 13%. Now, you should have been able to follow along with that pretty quickly just based on stuff that we've done before. But in this next calculation, you might want to pause the video here. So let's go ahead and do the covariance. All right. So we're going to multiply 15% probability. And what do we have? In that strong economy, asset A is going to generate 40%. That is 22% away from the mean. So we have 15% times the quantity, 40 minus 18, times the distance between the asset B's return, 20 minus its mean return of 13%. All right, so do you see what we're doing here? We have the probability of a strong economy, 15%, and then we're multiplying that by the distance between A's return and its mean and the distance between B's return and its mean. So watch what I'm going to do here. I'm going to take 15% times 22% times 7%, right? And then we're going to do that for the normal economy, and then we're going to do that for the weak economy. And so we get a covariance of 0.0066. Now, here's the fascinating thing about, oops, I didn't mean to do that. Here's the fascinating thing about covariance is that it can be 0. It can be positive and it can be negative, but it can be almost any number that is positive or negative. So it's really difficult to kind of determine and interpret what a covariance of 0.0066 truly means from an economic standpoint. One, we know it's positive, so we know that asset A and asset B's returns move together. They tend to move in the same direction. In other words, when one is positive, then the other one tends to be positive. But we need to make a better conclusion about its magnitude. I mean, we know that 0.0066 is pretty close to 0, but we might not be able to say just exactly how close to 0 it is. That's why we need to standardize the covariance. So look at this next equation. In the numerator, I have the covariance, which we just computed. And I'm going to divide that by the standard deviation of the first random variable times the standard deviation of the second random variable. When we standardize it by dividing by the product of the two standard deviations, we get another metric called the correlation coefficient. Now, what do we know about correlation coefficients? We know that their range is between a -1 and a +1. Now we can make some reasonable conclusions, not only about the direction of the relationship, but about the magnitude of the relationship. Now, what we want to do is we want to combine these covariances and variances as well. So look at the very bottom. I have what's called a covariance matrix. So we have two random variables, x and y. Notice down the diagonals, we have sigma squared sub x, that's the variance of x. And then we have on the next diagonal, sigma squared sub y, that's the variance of y. So in a variance covariance matrix, all of the variances are diagonal. And then on the non-diagonal components, you have the covariances, right? So let's drop down. So we have sigma yx, and then let's drop over sigma xy. So just like x covaries with y covaries with x, that's why you need a 2 measure to evaluate this kind of correlation or covariance. Now, of course, since we have covariance, second moment of the distribution, you're probably thinking that there's got to be third moment of the distribution. Of course, we call this Coskewness. And the cool thing about Coskewness, and we'll see this with Cokurtosis as well, is look in the first blue equations I have. With Coskewness, since it's the third moment of the distribution, and remember, we raise that difference to the third power, we still have to be sensitive to the third power. That's skewness. So notice we can have the skewness with xxy or the skewness with xyy. And if you look in the numerator of those two formulas, you'll see that we're going to square the difference between the first random variable and its mean, but we're only going to consider the difference between the second random variable and its mean just one time. And then we do the opposite for that second part there. Now, I will admit to this. During my life, in no exams did I ever have to compute Coskewness, but I have to interpret it. Now, lots of these statistical packages will produce Coskewness and Cokurtosis. So let's go ahead and focus on those bottom two block points. If two random variables exhibit positive Coskewness, they will tend to undergo extreme positive deviations at the same time. So that's where we're looking at the right-hand side of the distribution. If we generate lots of returns in security A, then we're likely to generate lots of returns in security B. But then, of course, the opposite holds true. If two random variables exhibit negative Coskewness, then they will tend to undergo extreme negative deviations. And this is important just to remember that with skewness, we're raising it to the third power. So we need to be sensitive to what happens on the right-hand side and what happens on the left-hand side of that distribution. Now, before I click over to the next screen, if I introduce Cokurtosis, you're going to say to yourself, all right, Jim, I know what this looks like. Of course, I know what this looks like, right? We can have Cokurtosis xxyy, or we can have it xxx and y. There's triple X. Let me give you a James Bond example. Do you remember in that great movie, The Spy Who Loved Me, Agent Triple X? All right. And then we can have X and triple Y. I don't think there was a triple Y agent in any James Bond movie. But notice that we've got a sum to 4, right? This kurtosis is the fourth moment. And so independent variables have a kurtosis of 1. But what happens if there is a high level of kurtosis, then what that means is that these random variables, if they are rates of return on a financial security, they are probably going to have extreme positive and extreme negative deviations at the same time. So do you see how these moments, those 4 moments of the distribution, right? And then their co-moments of the distribution, right? Coskewness, Cokurtosis and correlation or covariance, right? Do you see how these extra measures add an extremely important amount of knowledge to the number of seeds in the grapefruit on our table? I mean, imagine you pick up a grapefruit and you say, all right, just based on this, whatever people do when they feel the grapefruit and they shake it, they could say, oh, the mean is 5 and the Cokurtosis is 3, etc., etc. Then before you cut it open, you can make lots and lots of reasonable assumptions about how many seeds are going to be in this one and then how many seeds are going to be in its neighbor grapefruit. Grapefruit. So this is your homework assignment as you review these learning objectives. Think about eating a grapefruit.